All right, today we're tackling something pretty amazing, how chemists figure out what a molecule actually looks like. We're going to dive into one of the most powerful tools out there, NMR spectroscopy. It's really the gold standard for solving molecular structures, and it's kind of like learning a secret code. By the end of this, you'll know the basics of how to read it.
So, you've probably seen all those intricate drawings of molecules, right? The little balls and sticks all connected in complex ways. But have you ever stopped and wondered, how in the world do we know that's what they look like? I mean, you can't just pop one under a standard microscope and take a picture. So, how do they do it?
Well, here's the really cool part. They don't see it at all. They listen to it. Yeah, you heard me right. An NMR spectrum is basically a radio broadcast coming directly from the atoms themselves. It's a puzzle, a story, and once you learn the language, it tells you absolutely everything you need to know about the molecule's architecture.
So let's dive in. I want you to think of this whole process as a molecular puzzle. The spectrum we get from the machine is our puzzle box, and it's filled with all the clues we need. Our job is to learn the rules of the game so we can put all the pieces together.
And the official name for this game is nuclear magnetic resonance, or just NMR for short. The basic idea is we take our sample, we stick it inside a huge, powerful magnetic field, and then we sort of ping it with radio waves. Different atoms respond in different ways, but the most common and probably most informative type of NMR is proton NMR. It focuses specifically on the hydrogen atoms, or protons. So that's what we're going to focus on today.
Okay, here we go. Clue number 1. This is always the first thing you look for. It's the simplest step, but it's the foundation for everything that follows. Before we do anything else, we just need to know how many different kinds of protons are we even dealing with. So, you get your spectrum, and the very first thing you do is just count the number of signals or signal groups. It's that simple. Each one of those clusters of peaks represents a set of protons that are in a unique chemical environment. Now, if a molecule has any symmetry, all those protons that are equivalent because of the symmetry, they'll all show up together under a single signal. So, if you see 3 distinct signal sets, boom, you know for a fact there are 3 unique types of protons in your molecule.
Next up, clue number 2. Now that we know how many different types of protons there are, the next question is, where do they live? The position of each signal along that horizontal axis, which we call the chemical shift, tells us all about the little neighborhood each proton is in.
And the physics behind this is actually fascinating. See, every proton is surrounded by a cloud of electrons, and those electrons act like tiny little shields, protecting the proton's nucleus from the big external magnetic field. So if a proton is in an area with a lot of electrons around it, it's very shielded, and its signal shows up on the right side of the spectrum. We call that upfield. But if it's next to an atom that likes to pull electrons away, like an oxygen or a chlorine, that shield gets weaker. The proton is now de-shielded. It feels more of the magnet's pull, and its signal gets shifted way over to the left, or downfield.
Okay, so we've got how many types of protons, and we have a good idea of their environment. Clue number 3 is maybe the most straightforward piece of information we're going to get. How many protons are actually in each of those unique groups?
This is where something called integration comes in. The NMR machine is smart enough to actually calculate the area under each of those signals. And here's the key. The area gives you the relative ratio of the number of protons in each group. So if you have 2 signals, and the machine tells you their integration ratio is, say, 3:2, that means for every 3 protons of the first type, there are 2 of the second type. That's a huge hint. It might suggest you have a methyl group, a CH3, and a methylene group, a CH2.
All right, this next part, this is the aha moment. This is where the whole puzzle really starts to snap together. It's our final clue, and it can be the trickiest one to master, for sure, but it is by far the most powerful. This is where we get to hear the protons talking to their neighbors.
This conversation has a name, spin-spin coupling. Remember how we said every proton is like a tiny magnet? Well, that little magnetic field affects its neighbors. So a nice, clean peak that you might have expected to see gets split into multiple, smaller lines, or subpeaks. This splitting pattern is the ultimate clue for figuring out what's connected to what.
Let's just build this idea from the ground up, okay? Imagine you've got a proton, we'll call it proton A, and it has just one neighbor, proton B. Now that neighbor's tiny magnetic field has 2 possibilities, and it's a 50-50 shot either way. It can align with the main magnetic field, or it can align against it. So in half the molecules in your sample, proton A feels a slightly stronger field, and in the other half, it feels a slightly weaker one. The result? What would have been one peak gets split into two perfectly equal lines. We call this a doublet.
So what happens if our proton has two neighbors? Well, now there are more possible combinations. Both neighbors could have their fields aligned with the main field. That's one possibility. Both could be aligned against it. That's another. Or you could have one with and one against. And since there are two different neighbors, there are two ways for that to happen. So this creates three distinct magnetic environments with a probability ratio of 1 to 2 to 1. And that's exactly why we get a three-line pattern, a triplet, with that telltale 1-2-1 intensity ratio.
Understanding that physical origin, the why behind the splitting, is so important because it reveals this beautifully predictable pattern, and that pattern allows us to use a fantastic shortcut that saves us a ton of time when we're trying to solve a structure.
And that shortcut is the famous n+1 rule. It's really simple. A signal will be split into n+1 lines, where n is just the number of protons on the adjacent carbons. So if a proton has 0 neighbors, n is 0, so you get 0 plus 1, a single line, a singlet. If it has one neighbor, n is 1, you get 1 plus 1, 2 lines, a doublet. Two neighbors gives you a triplet. It follows directly from the physics we just saw.
And this logic just keeps on going. 3 neighbors will split a signal into a 4-line quartet. 4 neighbors makes a 5-line quintet, and so on. This table right here is basically your cheat sheet. You see a splitting pattern, you can quickly translate it into the number of neighbors that proton must have. Now here's a really important concept. This magnetic influence, this talking between protons, is not a one-way street. It is completely reciprocal. The effect that proton A has on proton B is exactly the same as the effect B has on A. And this gives us a powerful way to confirm that we're on the right track.
We measure this interaction with something called the coupling constant, or J value. It's simply the distance between the little subpeaks in a multiplet, and we measure it in hertz. So if proton A is splitting proton B and proton B is splitting proton A, the J value, that spacing, will be identical for both of their signals. Finding matching J values is one of the best ways to prove which protons are talking to each other. It's like finding matching fingerprints at a crime scene.
Okay, let's put it all together and see how this actually builds our final structure. We've collected all our clues, right? We know how many types of protons we have, we know what their environments are like, we know how many of each type there are, and we know exactly who their neighbors are. We have all the pieces. Now it's time to assemble the puzzle. And this is the systematic approach that every spectroscopist uses. You just follow these 4 steps, right in order. Each step gives you another critical layer of information. You identify one piece of the puzzle, like a signal for 3 protons that's a singlet and is far downfield, and you think, okay, that has to be a CH3 group next to an oxygen. Then you look for its neighbors and other connected pieces, and bit by bit, the full molecular structure reveals itself. It's really incredible when you think about it. By learning to listen to this atomic language, we can map out the invisible world of molecules with amazing precision. What starts out looking like just a bunch of confusing lines on a graph transforms into a clear, unambiguous blueprint of a molecule. And honestly, what we've covered today is just the first chapter. There are so many more incredible stories that molecules are just waiting to tell you.